class, object, abstraction, encapsulation. These are fundamental pillars of object-oriented programming. Before we move into complex features like inheritance and polymorphism, we must be very clear about these basics. A class can be understood as a blueprint or template, and an object is the actual instance created using that blueprint. Then comes abstraction, which means showing only the essential features to the user while handling the internal working details. After that, we study encapsulation, which means wrapping data and methods together and protecting the data from unauthorized access. Then these topics are highly important because almost every real-world application uses these principles. Whether you are designing a banking system, hospital system, or mobile app, you will always model entities as classes and objects. So today, let us understand these concepts clearly with the definitions, examples, and a simple C++ code. Now, let us look at the basic concepts of object-oriented programming. This slide lists the major concepts: class, object, data abstraction, and encapsulation, inheritance, polymorphism, dynamic binding, and message passing. These concepts together make OOP powerful compared to the procedural programming. In procedural programming, we focus mainly on functions and flow, but in OOP, we focus on entities and their behavior. First, we define a class, then create objects from it. Using abstraction, we show only necessary details and hide the complexity. Using encapsulation, we keep the data secure and allow controlled access. Then inheritance allows code reuse by creating new classes from existing classes. Polymorphism means one interface can behave differently based on the situation, which improves flexibility. Dynamic binding supports running decision making for method calls. Finally, message passing means objects communicate with each other by sending messages, similar to how components interact in real systems. So this slide gives a complete map of what OOP includes, and we will cover these step by step. Let us understand what a class is. A class is called the blueprint of an object. That means it defines what data an object will have and what operation it can perform. In C++, a class contains attributes, which are all data members, and methods, which are all member functions. A class is considered a logical entity. It does not occupy memory until we create an object from it. For example, think a class as a design of a house. The design itself does not occupy physical space, but when we build a house, it becomes real. Similarly, a class defines structures, but the object is the actual one that exists in memory. Classes are used to model real-world entities like student, employee, car, bank account, etc. When you design a software using classes, your program becomes modular and easier to maintain. So always remember, class is a template that groups related data and functions together in a single unit. Now, what is an object? An object is an instance of a class. It represents real-world entity and it occupies memory. This is a key difference. Class is logical, object is physical in memory. For example, if you have a class called student, then student 1, student 2 are objects. Each object has its own copy of data member like name, roll number, marks, etc. But they all share the same structure defined by the class. Objects are created to actually use the class in the program. When you create an object, you can access its attributes and call its methods using the dot operator. This is how object-oriented programs works, by creating objects and making them interact. So, in real applications, thousands of objects may be created, like users, transactions, products, etc., each representing one entity. Now, let us look at the general syntax of a class in C++. A class contains three important components: data, members, member functions, and access specifiers. So, data members represents the variable inside the class. Member functions represents the behavior or operations. Access specifiers decide which members are accessible outside the class. The common specifiers are public, private, and protected. If a member is declared as public, it can be accessed from outside the class using an object. If it is a private, it cannot be accessed directly. Only methods inside the class can access it. Protected is mainly used for inheritance. So when you write a class, you must decide what should be visible to the outside the world and what should be hidden from security. This concept is strongly connected to encapsulation, which we'll learn later. Let us understand the student class example given here. The student class has public data members called roll and a member function called show, which prints the roll number. In this main function, we create an object S of class student. Then we assign roll number 101 using S dot roll equal to 101. After that, we call the method using S dot show. This is very simple example, but it clearly shows how class and object work. The class defines the structure and the object is used to store the data and call methods. One important thing you should observe is, since role is public, we can directly modify it from main. But in real application, direct modification is not recommended because it reduces security. That is why later we use private data members and protected and provide setter and getter methods. This slide visually explains the relationship between class and objects. It shows that a class is a category and objects are the real time under that category. For example, student is a class, John, Sophie, and Lily can be objects. Each object has its own states such as name, age, and other attributes, but all objects follow the same structure. The slides show the difference between states and behaviors. States are attributes like name and age, and behaviors are action like eating, running, drinking. In OOP, we design software by identifying the classes, their states, and behaviors. Then we create objects and make them interact. This approach helps us to build systems that are close to real world thinking. Now let us understand abstraction. Abstraction means showing only the essential feature and hiding the implementation details. In other words, it focuses on what the object does, not how it does it. The slide gives an example using an abstraction class shape, where the method area is declared as a pure virtual function. This means shape is an object class and it cannot be instantiated directly. Only derived classes like circle, rectangle, etc. will implement the area method. In real life, abstraction helps us reduce complexity. For example, when you drive a car, you use the steering, accelerator, and brake. You do not need to know the internal engine mechanism. Similarly, in programming, abstraction provides a simplified interface for the user and hides internal logic. This slide gives a real-world example of abstraction using an ATM machine. When you use an ATM, you only see the interface. Insert card, enter PIN, withdraw cash, check balance. You don't see how ATM connects to the bank server, how it verifies the PIN, how it checks your balance, or how it counts the cash internally. All that complexity is hidden from the user. This is exactly what abstraction does in software. It hides internal details and provides a simple interface. This makes the system easy to use and reduce the changes of user errors. Now we come to encapsulation, which is one of the most important OOP principles. Encapsulation means wrapping data and members together into a single unit, which is a class. It also means protecting data from misuse by restricting direct access. This is achieved using access specifiers like private. The example gives an account class where balance is private. To modify or read balance, we use public methods setBalance and getBalance. This ensures controlled access. For example, we can validate the input in setBalance and prevent negative balances. Encapsulation improves security and prevents accidental modification of important data. It also improves maintainability because changes in internal data representation do not affect in external code. This slide provides a complete C++ demonstrating encapsulation. The account class has a private variable balance. The class provides public methods setBalance and getBalance. In main, we create an object ACC. Then we set balance using ACC dot set balance of 5000 and display it using ACC dot get balance. This program shows how private member cannot be accessed directly from outside the class. If you try at ACC dot balance equal to 5000, it will give an error. That is an advantage of encapsulation. In real world system like banking, you never allow direct access to balance. You provide functions like deposit, withdraw, check balance, etc. that ensures proper validation and security. Now let us discuss the benefits of encapsulation. This slide lists three key benefits: data security, controlled access, and code maintainability. First, data security. When variables are private, no external code can modify them directly. This prevents unauthorized access. Second, controlled access. We provide public methods to access data, so we can control how data is updated. For example, we can prevent invalid values, enforce constraints, or log changes. Third, maintainability. Encapsulation makes code easier to modify and maintain. If we change internal data representation, we only update the class methods, not all places where the data is used. Next is inheritance. Inheritance is a process by which one object acquires the properties of another object. In C++, this means a derived class inherits data member and member functions from a base class. Inheritance supports code reuse and creates a hierarchical relationship. The slide shows an example using mammals, dogs, cats, humans, and further subcategories. Similarly, in programming, we can have a base class vehicle and derived classes car, bike, truck. Inheritance helps avoid duplication. Instead of writing common code again, we write it once in base class and reuse it. However, inheritance should be used carefully. Overusing inheritance can make the design complex. In modern design, we use inheritance only when there is a clear is relationship. Now we discuss polymorphism, which means many forms. Polymorphism allows one interface to be used for a general class of functions, and specific action depends on the situation. For example, the same function named draw can behave differently for different shapes like rectangle, triangle, and circle. The interface is same, but the implementation differs. Polymorphism improves flexibility and supports dynamic behavior. It is commonly used in real-world applications where we want general code that works for multiple object types. There are two types: compile-time polymorphism using function overloading and operator overloading, and runtime polymorphism using virtual functions. Dynamic binding is closely related to runtime polymorphism. Binding means linking a function call to the function definition. In static binding, the method to be called is decided at compile time. This happens in function overloading. In dynamic binding, the method to be called is decided at runtime based on the object type. This happens with virtual functions. For example, if you have a base class pointer pointing to a derived class object, the method call will be decided at runtime. That allows flexibility and supports real-world behavior. Dynamic binding is important because it enables late decision making. It allows the program to choose the correct method based on actual object type during execution. Now we come to message passing, which is how objects communicate in OOP. In object-oriented system, objects interact by sending messages to each other. A message can be understood as calling a method of another object. For example, object A calls a method of object B, which means A sends a message to B. This communication is essential in real-world applications. For example, in a banking system, an account object may send a message to transaction object. In a shopping app, cart object communicates with the payment object. Message passing supports modularity and loose coupling. Instead of writing one big function, we create multiple objects and allow them to interact. Finally, this slide summarizes methods for access: getter methods, setter methods, and controlled modification. Getter methods are used to read private data safely. Setter methods are used to modify private data with validation. This ensures controlled access to sensitive information. For example, in account class, get balance returns balance and set balance update balance. In real systems, set balance may check if the value is valid, or it may restrict updates based on the rules. This is a core technique used in encapsulation. As a best practice, we should keep important variables private and access them only through public methods. With this, we complete data explanation everything in today's session. Thank you.